Hey everybody, we are going to look at a kind of a cool thing. We're going to look at second order, homogeneous, ordinary differential equations with constant coefficients and how do we solve them. And here's the coolest thing, you can solve it in your head. Hey, let me tell you what all this stuff means. First of all, second order. What that means is we're going to be dealing with differential equations involving second derivatives. In our class, up until this point, all of our derivative equations, differential equations, have been first order. They've just been based on a first derivative, dp dt or something like that. Now, we're going to have a second derivative. And because we're dealing with second derivatives, the prime notation is just a little bit more easy to work with than our Leibniz notation, like a dy second derivative kind of notation is a little bit crazy. So y double prime. So second order also has a first derivative, also has the function itself y. So this is a second order differential equation. It's homogeneous. What that means is all the terms of this differential equation are based on either y or its derivatives. Notice y second prime, y prime, y. There's no term in here involving, say, an independent variable t or x or whatever the variable might be. So it's homogeneous. It's an ordinary differential equation. That's a phrase often used. I don't know if we've used it so much in our class, but ordinary differential equations versus partial differential equations. You'll get to that in another course. Partial differential equations. But this is an ordinary differential equation, and it has constant coefficients. A coefficient of 1 on that second derivative term, a coefficient of -5 on that first derivative, and a +4 on y itself. So it's a second order, homogeneous, ordinary differential equation with constant coefficients, and I say you can solve it in your head. Yeah, watch this. Can you think about a function? No, well, let me back up. What has been the goal of differential equations from the get-go? The goal has been to find the function, say f of x or y of t or p of t or whatever it was, find the function such that the rate of change was what it was. You know, if we had an autonomous differential equation like dp dt equals 0.8p, the goal was to figure out some relationship between p and t. Whether we made graphs, whether we did Euler's method, or now, you know, Runge-Kutta, or whatever the case may be, separate the variables, or if we did that reverse product rule, whatever it was, the goal was to get the function given its rate of change. Likewise, the goal here is to figure out how does y work, what's the relationship between y and its independent variable, given that the second derivative of y, the first derivative of y, and y itself must somehow combine and make 0. I'm pausing because right now your brain should be on fire. You should be thinking, what function y would I be able to take its second derivative, its first derivative, the function y itself, and combine them to get 0? Will you do me a favor? Will you pause the video right now? And will you just think this through? And I'll bet you, because it always happens, if we were in the classroom right now, somebody would figure this out. There is a function. There's y, let's just say y as a function of t is our goal. There is a function so that its second derivative minus 5 times its first derivative plus the function itself all combine to make 0. You'll figure it out. Pause and come back. I hope you paused and came back, and I hope you figured something out. And what I hope you figured out is that the only kind of a function that you could be dealing with in this case is an exponential function. Here we go again, kind of like the reverse product rule, that exponential function kind of plays a cool role here. Only as something like an e to the x can you take its second derivative. Can you take its first derivative? Can you take y itself and combine them in some way and get 0? Now, when you're working on that, you may have figured out that you needed some coefficient in that exponent, though. By the chain rule, you needed something, I'll call it r. We needed some coefficient on x in that exponent, so that when you took the second derivative by the chain rule and the first derivative times 5 and the function itself times 4 all combined and made 0. So I'm going to claim that the only way, let me write this down, the claim is the only way that this can happen is if the function is y equals e to the something x. Okay? Well, if that's true, then y prime is equal to r times e to the rx. Keep in mind the derivative of e to the stuff is e to the stuff. Chain rule says the derivative of rx is r, so by the chain rule we get this. And the second derivative, the derivative of the derivative, would also be e to the rx. But when we take the derivative of the stuff and get r again, times the r from the first derivative, we'll get r squared. So what we're going to do now is take this claim. We know that the function we're dealing with must be of the form e to the something x. Let's figure out specifically what the something would be. Here's how. What has to be true is that y double prime, that is r squared e to the rx, minus 5y prime, that is minus 5 times r e to the rx, plus 4y, that is 4 times e to the rx, can combine and make 0 if we get the right value for r. Now look at here, algebraically speaking, we've got a term involving e to the rx, we've got a term involving e to the rx, we've got a term involving e to the rx. Let's factor out that common factor. Let's factor out e to the rx. Now if you factor it out, what's left here in this term is r squared. What's left in this term? Minus 5r. What's left in this term? Plus 4. Now, if you're not smiling right now, something's wrong, man. You should be smiling because there's something very familiar about this. We've got an e to the rx being multiplied by a quadratic to produce 0. The only way you can multiply this factor times this factor and get 0 is if one of the two factors or both are 0. Now, e to the power of rx, there is no value of r or x that will make e to the rx 0. This thing right here can never be 0. So the only way this product can be 0 is if this quadratic is 0. So let's focus on this. Now you have a quadratic. You learn like in Algebra 1 how to solve a quadratic. You can factor, there's the quadratic formula, certainly get on Desmos, graph it, look for those zeros. But since I'm here on a whiteboard, I'm going to go old school, and I'm going to try factoring this quadratic. For sure, r times r will get me the r squared. Now I need to get these two terms to multiply to get 4 while they add to make 5. Well, for sure, 4 and 1, I think it'll be a minus and a minus. Let me check that out. R times r squared, yay. Minus r, minus 4r, minus 5r. Yay! Plus 4. Perfect! So now, this times this is 0. Well, this product will be 0 if r equals 4 or r equals 1. There you go. So back to the big picture, our claim was that this second order differential equation can only combine and make 0 if you have an exponential, and now we know that it actually happens in two cases. We now know that if y equals e to the 4x, or if y equals e to the 1x, we know we got this thing done. Now, there's some more work we have to do here, but I'm going to pause here because this video is long enough already. I'm going to pause here, let you think this through a little bit, play the second video and see where we're going to take this.